Thank you for the introduction. My talk is about FANCI, a system for the detection of domain generation algorithm malware based on machine learning. And to get started, I first take a look at traditional botnet communication. And here you have usually two simple approaches. Either to use fixed IP addresses or fixed domain names, but from Botmaster's perspective, there's a major drawback. Once these values are known to a defender, it's rather easy to block for a defender, and by this block the communication of the bot with the C2 server. And that's the reason why modern botnets more and more often rely on domain generation algorithms, DGAs, and a DGA is a pseudo-random algorithm generating rather large sets of domains, which are then subsequently queried by the bot to eventually contact the C2 server. And as typically the botmaster only registers a small subset of the generated domains, the major part of these generated domains result in NXDomain responses by the DNS system. And that's why it's a very good idea to take a closer look at this specific part of the DNS traffic to detect domain generation algorithm malware. But if you record such traffic at a larger DNS server, you will not only see DGA-related traffic, but also NXDomain responses caused, for example, by typing errors or misconfigured software or DNS misuse. And that yields us our challenge here, and the challenge is to classify these non-existent domains into benign domains and DGA-related domains. Here you see some examples how this could look like, and if we perform classification here, the result would look like this, where the green ones are benign domains and the red ones are known DGA-related domains. And as you can see here, it's not always intuitive to determine whether a domain is DGA-related or not. And to tackle this problem, we present our system FANCI, feature-based automated NXDomain classification intelligence. And FANCI is a system performing machine learning-based classification of NXDs into benign and DGA-related. FANCI performs this classification with very high accuracy, is lightweight and efficient, and the classification itself is performed on domain names only. That means no metadata is required for the classification itself. And FANCI is furthermore generalizable and therefore usable as a service. With the help of FANCI, we are able to find DGA-based malware-infected devices and deliver actionable IOCs. Next, I give you a short overview about the system FANCI itself, starting with the architecture. And FANCI consists mainly of three modules: the training module, the classification module, and the intelligence module. And the training module takes labeled data as input, performs the training, a supervised machine learning classifier outputs a model, which is then used by the classification module to perform the actual classification of previously unlabeled NXDs. The intelligence module can be used to process full NXDomain responses. That means full DNS packets and not only domain names. And the intelligence module performs a pre-processing, uses the classification module to to assign the label to an NXD, and then stores the results in a database and provides IOCs or processed result views for security analysts. Next, we take a closer look at the classification parts of FANCI itself, FANCI users, and we use a supervised learning classifying approach. That means we require labeled data as input for our training, in our case labeled domain names, so DGA-related domain names and benign NX domains. We perform a feature extraction and then perform the training. And with the output model, we are then able to predict unknown domains and assign a label to them, so whether they are DGA related or not. And next I give a short overview about the features we used within FANCI. Here I present 3 examples. In general, a feature is simply a mathematical function taking an input value, in our case that's only a domain name, and then outputting a numeric value. And FANCI uses 21 features overall, where you can distinguish 3 categories here. The structural category, where FANCI uses 12 features, 7 linguistic features, and 2 statistical features. And if we take a look at the examples here, for example, the valid top-level domain feature is an example for a structural category. The alphabet cardinality is an example for a linguistic feature and outputs an integer. And the entropy, according to Shannon, is an example for a statistical feature and outputs a rational value. And now that we have seen what FANCI wants to achieve, namely performing classification of NX domains into DGA-related and benign, I present to you our evaluation and including a real-world application test. First, I present our data sets we used for our laboratory experiments. And as we require labeled data, we see here 3 data sources. The first one is from the central DNS server of University of Aachen. And here we were able to record 31 days of DNS and NX domain traffic and obtained 35 million unique benign NX domains. Our second data source is the central DNS infrastructure of Siemens AG, and here we recorded 61 days and obtained 31 million unique benign NX domains. And for our DGA-related domain data source, we had access to DGArchive, which is a database maintained by Fraunhofer from Germany. And this database contains about 50 million unique DGA domains of 1,344 days of more than 70 different DGAs. And based on these data sources, we performed in the first step of our evaluation a search for the best classifier for FANCI. And for this reason, we compared support vector machines and random forests in mainly 2 different categories of scenarios. The first scenario assumes that we use 1 classifier per known DGA, and that could, for example, look like this. We use for training domains from DGA1 and combined with benign NXDs from the university network, and then perform the classification on DGA1 and benign NXDs from the university network. The second scenario assumes that we use 1 single classifier trained with domains of multiple different DGAs. And this could, for example, look like this. We train our classifier using domains from DGA1 to N, combined with benign NXDs from the university network, and then perform classification on different domains of the same DGAs and benign NXDs from the university network. And the result of this search for the best classifier was that the best performing classifier is a single random forest classifier trained with all known DGAs. And to get an idea of how well this classifier performs, I present in the following 3 experiments from our laboratory evaluation. And the first experiment had the goal to test FANCI's capabilities in detecting domains of known DGAs. For this, we performed 5-fold cross-validations on 20 data sets of size 100,000 and performed 5 repetitions with fresh folds, which results in 500 passes overall. And for this test, we performed training and testing using benign NXDs from the university network and domains from DGA1 to N, overall 59 different DGAs. And the table below shows a statistical summary of our classification performance, including the accuracy, the true positive rate, and the false positive rate. And you can see here that the accuracy is beyond 99%. The true positive rate is also beyond 99% at a very low false positive rate, which allows us to conclude that FANCI is able to detect known domains of known DGAs with very high accuracy. The second experiment had the goal to test FANCI's capabilities in detecting domains of previously unknown DGAs, and for this we again used 20 datasets, 20 fresh datasets of size 100,000, and performed a leave one out evaluation for 59 different DGAs, which results for each of the 20 datasets, which results in 1,180 passes overall. And this could, for example, look like this in a single pass, that we train our classifier using domains of DGA2 to N and benign NXDs from the university network, and then try to predict a data set consisting of domains of DGA1 and benign NXDs of the university network. The table below again shows a statistical summary of the results, and it's important to note here that the accuracy is slightly lower than in the experiment before, but only because the true positive rate is slightly lower. The false positive rate is almost the same in this experiment, which means that in worst case we may miss some unknown domains, but we do not increase our false positive number of false positives. The third experiment I present is to test how well FANCI generalizes. That means we wanted to test if it is possible to perform the training in network 1 and then deploy FANCI in a second unknown network. And for this we again use 20 data sets of size 100,000 in this case per benign data source, and perform the cross-validation, resulting in 400 passes overall. And this could, for example, look like this, that we perform training using domains of DGA1 to N and benign NXDs from the university network, and then performed the testing on DGA1 to N, but with benign domains from the company network. And on the right-hand side, the same experiment vice versa. And the tables below again show statistical summaries of the classification results. And as you can see here, the accuracy and true positive rate are comparable to the experiment, to the first experiment, where we trained and tested with benign data from the same network. Only the false positive rate slightly increases, but is still very small. And so we are able to state that FANCI can be used within a new network in which it was not trained on. And yes, exactly. And the last part of our evaluation is a real-world application test. For this, we obtained a fresh data set from the university network of NXDomain responses we recorded 31 days again, and obtained 35 million unique NX domains, and performed all tests on single-threaded on consumer hardware. And for our real-world application test, we trained a fresh random forest classifier using a set size of 100,000, and then used this classifier to predict all 700 million NX domain responses we recorded, which is equivalent to, on average, 164 NX domain responses per second. And due to our performance measurements, FANCI is able to perform 400 samples, to perform prediction for 400 samples per second, which allows us to conclude that FANCI is, in terms of performance, real-world applicable. The main result of our real-world application test is that we are able to report 10 groups of unknown DGA-related domains. Overall, we found 405 unknown DGA domains. And here you can see six examples, 6 example groups, where the upper 3 groups are probably completely unknown DGAs, and the lower 3 groups are probably variants of known DGAs or unknown seeds of known DGAs. And The attribution in this case was performed using our domain knowledge and the DGA-Archive, because we had no ground truth in this experiment, of course. And it's noteworthy to say here that the diversity is very high. If you, for example, take a look at DGA 1, 2, and 4, which look almost completely random, and compare this, for example, to DGA 3, which looks more like a hexadecimal string with a fixed prefix, you can see that FANCI is able to detect DGA domains independent of the generation scheme. And the DGA 5 and 6 group are generated using dictionaries. In summary, FANCI is a system classifying NXDs into benign and DGA-related. Its classification is based on domain names only. It performs lightweight, efficient, and high accurate classification. FANCI is real-world applicable, and we were able to report 10 groups of unknown DGA domains. And FANCI generalizes very well and is therefore usable as a service. Thank you. Are there any questions?
Any question? Okay, let me start with a question quite similar to the previous one. So I also truly believe that your approach can identify new real-world, I'll say DNG algorithm in general. And you also demonstrate this really work. But do you have any concern about using machine learning in your approach? For example, what if you're the attacker? Can you come up with the best domain generation algorithm that bypass your scheme?
Yes, very good question. Yes, of course, if you have domain knowledge about how domain generation algorithms work, you probably are able to invent a new generation scheme which was not used before and which we have not seen before, and then are very probable you will be able to bypass our detection. But you have to say that we considered 4 different generation schemes, which are first an arithmetic generation scheme based on random numbers, then hash-based generation schemes, wordless generation schemes, and permutation generation schemes. And once we have seen such a DGA of a certain generation scheme, we were able to detect it. So it's only a small you only have a small amount of time you can use your DGA and bypass our detection, because once we have seen it, we can train our model and then it's able to detect it.
Your name and affiliation.
Sure. Hi, Matt Elder, Johns Hopkins, APL. It's great work. I had a question regarding your evaluation and its implications on deployment. So I would characterize the evaluations you did as spatially, taking out, checking the applicability of one data set on the data coming from another site. Did you consider doing any temporal evaluation where instead of you would split your data set, train on the first half of it temporally, and then evaluate on the second half? And that relates to a deployment model for this on how often you think you'd have to retrain your model if this were deployed.
For benign data, we didn't consider that, but for the DGA data, we did. So there are several DGAs that are time dependent, okay. And we performed a evaluation to check whether our classifier is able to detect the same DGA when it's 1 year ahead or so, and there was no problem. And I think regarding the benign domains, it's there is probably sometimes a retraining necessary, but first it's very fast, so you can retrain the model within minutes. And second, you have probably only to retrain if you know there's something changing in the network. So you probably will know when you have to retrain before. So.
Okay, thank you.
Let's thank our speaker once more.